Hey everyone, and welcome. Today, we're going to tackle a really fundamental piece of modern electronics, the bridge rectifier. We're going to break down exactly how this brilliant little circuit takes the AC power from your wall and turns it into the DC power that, well, pretty much every device you own actually runs on.
Electro knowledge. Power up your concepts.
So let's just start with the basic problem, right? The power that comes into our homes is alternating current, or AC. The electricity is constantly switching direction, back and forth. But all the sensitive electronics, inside your phone, your computer, they need a nice, steady, one-way flow. That's direct current, or DC. So how on earth do we bridge that gap?
And the difference couldn't be more stark. See, AC is fantastic for sending power over really long distances. Think power plant to your house. But DC, that's the language that all our modern tech speaks. It's the language of microchips and processors. So to make literally anything work, we have to do this conversion.
And that's where this thing called a rectifier comes in. You can think of it like a one-way valve or a one-way gate for electricity. Its entire job is to take that kind of chaotic back-and-forth flow of AC and force it into a disciplined, single-direction DC flow.
Now, the most popular and, frankly, most efficient way to do this is with the full Wave Bridge Rectifier. It's so elegant. It just uses 4 simple components called diodes, and it arranges them in this clever bridge shape. And what makes it so great is that it uses the entire AC wave, both the positive and the negative swings. Plus, and this is a big one, it works with a regular, standard transformer, which makes it super practical and cheap to build.
Okay, let's get into the weeds and actually see how this thing works step by step. We're going to start by tracing the path of the current during just the first positive half of that AC cycle.
All right, so in this first phase, the top terminal of our AC input is positive. Now, this electrical pressure starts pushing on all 4 diodes, but diodes, they're like one-way streets. If you push from the right direction, they let current right through. We call that forward biased. So in this case, D1 and D2 basically turn on. Current flows out of the source, through D1, down through our load, that's the thing we're trying to power, and then completes the loop through D2. At the same time, that pressure is hitting D3 and D4 from the wrong direction, so they're reverse biased, and they just act like closed gates. No current gets through them.
Okay, so pause here for a second. The most important thing to notice is the direction of the current. It's flowing down through our load. Go ahead and burn that direction into your memory.
But AC stands for alternating current, so that input is about to flip. Let's move on to the negative cycle and see how this clever circuit maintains the flow.
So, just like we said, the AC source flips polarity. Now the bottom terminal is positive. The pressure is coming from the opposite direction. But this time, guess what? Diodes D3 and D4 are now pointed in the correct direction to be forward biased, so they turn on. The current flows up from the source, through D3, over to our load, and back to the source through D4. And of course, now D1 and D2 are facing the wrong way, so they're reverse biased and they shut down.
And this right here, is the magic of the whole thing. Take a look. Even though the AC input did a complete 180-degree flip, look at the direction of the current going through our load. It is still flowing down. It's the exact same direction as before. The bridge ingeniously rerouted the flow to keep it perfectly consistent.
So what does this constant one-way flow actually end up looking like? Well, this is where we get our result. A brand new kind of waveform we call pulsating DC. And really, this is the whole point of the exercise. It doesn't matter which way the AC input is swinging, positive or negative, the current going through our load is relentlessly, always, flowing in just one direction. What we've essentially done here is we've taken that negative half of the AC wave, which would normally go below the line, and we've flipped it up to be positive. So the output is just this series of positive bumps, or pulses. And because the current never actually reverses, we call it pulsating DC. And here's a really interesting side effect. The frequency of these pulses is now double the input. So if you put 60 Hz AC in, you get 120 Hz pulsating DC out.
Now, there's a reason this design is absolutely everywhere in electronics. So let's look at the specific engineering advantages that make the bridge rectifier so incredibly popular and useful.
So, let's compare it to its main rival, the center-tapped rectifier. Yeah, the bridge uses 4 diodes instead of 2, but, and this is a big but, it lets us use a simple, standard transformer which is way cheaper and smaller. Now, check out peak inverse voltage, or PIV. That's just how much voltage a diode has to block when it's off. In our bridge circuit, that stress is half as much, which means our diodes don't have to be as beefy. And finally, the transformer utilization factor. That's just a fancy way of saying it gets more power out of the same size transformer. It's just plain more efficient.
And the numbers really back this up. The maximum theoretical efficiency here is 81.2%. That is literally double the efficiency of a much simpler halfway design, which just throws away the entire negative part of the AC wave. This design wastes way less energy.
So what does all that technical stuff mean in the real world? Well, it means you get to use a cheaper, smaller transformer. The lower stress on your parts means they're more reliable and last longer. Better efficiency means less wasted energy, which means less heat. It all adds up to a compact, robust, and really economical solution.
And hey, you don't have to take my word for it. This quote from the website Electronics Tutorials just nails it. The main advantage of this bridge circuit is that it does not require a special center tap transformer, thereby reducing its size and cost. That one little design choice makes everything smaller and cheaper. It's a huge win.
So we did it. We successfully created a one-way street for our current. But there's a catch. The output is still this series of pulses, right? It's bumpy. It's not that smooth, flat line of DC that our electronics really need to work properly. And that leads us to the next logical question. What component do we have to add to this circuit to smooth out all those bumps and get a truly stable DC voltage? Well, that's a topic for another day.
Thanks for watching. Like, share, and subscribe to Electro Knowledge for more electrical concepts.